Good evening, everybody, and welcome to tonight's nanoTalks. My name is Luca, and it's my pleasure to guide you through this evening tonight. But before we delve into this really interesting topic of water, I would quickly introduce you to what the nanoTalks are and what you can expect from this evening. The nanotalks aim at giving young researchers an opportunity to present their science to a broader audience. We want to put the science that they're doing into perspective. And this is also really the goal of the think tank that is behind the nanotalks, REACH. We are a Swiss think tank that tries to work for a science-friendly culture where science and society try to solve the problems of today and tomorrow based on evidence. If you are interested in participating in the nanotalks or helping the goal of REACH, you can always join our community, either by being active or just as a passive member signing up for the newsletter. So I recommend you now or after the talks to sign up for our newsletter. Also, as you might know, interaction is really a key point for us, and as we're doing these live streams now from the studio or, well, Joel's living room, we want to still maintain some sort of interaction with you. So at the end, after the two talks of tonight, we'll have a Q&A. For that, you can go to sly.do and enter the code nano-water. So there you can ask your questions under the Q&A button, and in the end we'll discuss them together. But now, after my short introduction, we're ready to go for our first speaker. I would like to introduce you to Céline, who is here with me in the studio, and she's from the Water Research Institute, Eawag, and she's going to talk about how we should really reconsider how we think about wastewater. So Céline, the stage is yours.
Hello everyone, thank you for joining my presentation tonight. I'm Céline, a postdoc researcher at Eawag, the Swiss Federal Institute of Science and Technology. And like Lucas said, the aim of my talk is to show you that wastewater can be a resource. So this concept is not obvious to accept because in our daily life, when we flush the toilet, we don't necessarily make the connection between the flush water and a nice shower, or even a glass of drinking water. Yet, we live in a resource-restricted environment and the population is growing, so we have to deconstruct our misconception about wastewater and understand that it's urgent to see it as a resource. The deconstruction is, however, difficult. Wastewater is not the most glamorous topic ever, so it's smelly, it's disgusting. It's not the type of topic you bring to make new friends at a dinner, especially at a dinner. So why is wastewater so taboo? It's because since centuries and still now in most of the city, we have a linear water management scheme, meaning that we withdraw the water from the environment, a lake, a river, groundwater, and we treat it through the wastewater treatment plants to supply the city. After consumption, wastewater is collected. At this point, most of the consumers only have a vague idea of what is happening with wastewater. And the fate of wastewater is linked to what it contains. So wastewater is made of water, carbon, nitrogen, and phosphorus. It also contains bacteria, viruses, or other chemicals, but today I really want to focus on these four constituents. And because of the presence of carbon, nitrogen, and phosphorus, we cannot return the water directly to the wastewater directly to the environment, and this is why we need a treatment. And the goal of the wastewater treatment plant is to remove carbon, nitrogen, and phosphorus. So carbon and nitrogen are removed as gaseous waste using biological process, and phosphorus is eliminated as a solid waste through biological and chemical processes. After treatment, we return to the environment a good quality water. To give you an idea, each day, each person consumes 150 liters. And if we scale up, we take the example of Switzerland, it's 500 million cubic meter per year, the equivalent of 150,000 Olympic swimming pools of good quality water which are returned to the environment instead of being used as a resource. And in fact, we already use it as a resource, but indirectly, because the city downstream will use the river water as a drinking water source, but it contains already treated wastewater. And to treat this resource, we use another resource, energy. 0.5 billion kilowatt hour per year is used for water treatment, the equivalent of the energy consumption of 90,000 households. And the energy is not only used to return a resource to the environment, it's also used to degrade other resources, carbon, nitrogen, and phosphorus. For example, nitrogen and phosphorus are used in agriculture already. So we see that this linear water management stream is not sustainable anymore in a resource restricted environment. So it's important to find ways to recover this resource to our needs as a society, but also to limit our impact on the environment. So what are the solutions to do that? Well, one solution is to rethink our buildings. So I introduce you to the example of the Nest. The Nest is the research and innovation building of EMPA and Eawag, located at Dubendorf. And the concept behind the Nest is that, contrary to conventional buildings, you have, we don't see it here, but you have a fixed central part. And on these fixed central parts, you have these concrete platforms where you can plug and unplug units based on the material, technologies, or space needs you have for the building. And this building is really interesting in terms of water management. So instead of having only one wastewater pipe, like in conventional building, in the Nest we have different pipes for different types of water usage, and the treatment is made on site to use the valorization products for the building needs. So what kind of stream do we have? The first one is grey water, coming from the water we use for shower and kitchen. Then we have black water coming from the feces, and finally yellow water coming from, well, the urines. This is what we call source separation, and it's very interesting because it simplifies the recovery of the water, carbon, nitrogen, and phosphorus. So how do we valorize them? I will start with grey water. And grey water, it's mainly water. So it's around 65% of the wastewater we generate, but it contains only diluted soap or grease. So it's a very good candidate to recycle the water in the building. There are different types of technologies implemented to treat grey water. Often they are implemented in series. And I want to present you one of them because it's often used for grey water treatment, and it's one of my specialty. So it's this. So it's not just a random piece of paper I grab on the table, it's a membrane. So you have flat sheet membranes, and you also have like these tubular membranes or hollow fiber that look like spaghettis. And so what is a membrane? A membrane is a porous material used as a physical barrier implemented to filter the water. So when you have a water which contains contaminants, you can filter it through the membrane by using by the help of a pump, which will apply a pressure. And the quality of the treated water, the filtered water, depends on the pore size of the membrane. So for example, this bacteria is bigger than the pore size, so during filtration it will be rejected by the membrane, while smaller molecules like water pass through the pores. So this process is really interesting to produce high quality water. However, there is always a but. Bacteria tends to accumulate onto the membranes, and gradually they will clog the pores. And the clogging is even worse because of the pressure of the pump that will really compact this biofilm. So at some point, water is not passing through anymore. And to prevent that, we use chemicals. So membrane, even though if it's interesting, we need chemicals, we need energy. So this represents a price, and this will consequently increase the bills of the inhabitant of the building. So how do we decrease the bills? Well, at Eawag, now we are trying to see if it's possible to remove the pump and use gravity or ultra low pressure for filtration. So this way we don't need energy anymore. And we also want to stop using chemicals and just accept that bacteria grow on the membrane. And when we stop the maintenance and when we don't have the pump anymore, what's happening is that the biofilm is getting porous in comparison with the conventional membranes, and water channels are formed here, which allows water filtration. So filtration is a bit slower than conventional systems, but if we increase the surface of membranes, we can produce big amounts of water. And another very interesting point, by letting the biofilm be, so the bacteria be, is that we can work with them. Because bacteria, they consume some molecules which we don't want in the filtered water, but that without bacteria, with the classical membrane, they will just pass through. So this system is cheaper and produce higher quality water. So this is well studied for drinking water, and now we are trying to implement this for grey water. And I just started the experiment yesterday, so we will see how it's working. Now, what do we do with black water and yellow water? Well, before doing something with it, we have to separate them. And to separate them, well, we need toilets. And these toilets are not conventional toilets, they are source separation toilets. So, how do they work? In the back here, we collect the feces with the water, and the feces is the main source of carbon in wastewater. So in the basement of the building, the idea is that we separate the water and the feces, we press the feces, and then we obtain these pellets. And these pellets can be used for the heating of the building. In front of the toilets, we collect the urine, which is the main source of nitrogen and phosphorus in wastewater. And Eawag worked on the development of a process to stabilize, concentrate, and disinfect the urine. And the final product of this process is Aurine fertilizer. So this fertilizer is now commercialized and produced by Vuna company. Vuna company is a spin-off of Eawag. And it's really interesting because since 2018, this fertilizer is licensed as a fertilizer by the Swiss Federal Office of Agriculture. So you can grow flower, but you can also grow vegetables with this fertilizer. There is no human risk associated to it. So with urine, we can basically supply fertilizer for agriculture. So we saw that it is worth to change our mind or to rethink the way we build buildings, and also to change our mind about how we see wastewater and how we manage it. So in wastewater, we can, if we separate the wastewater, we can use grey water to produce water for the city needs or agriculture. From the feces, we can produce pellets for energy recovery. And finally, the urine can be used for fertilizer production. So we see that it makes sense to take wastewater as a serious society topic, but it also makes sense to take it sometimes a bit less seriously, like we did during our research group did during last Eawag Christmas party. And I believe that it's really important to make fun about wastewater because it helps us to spread the word about its interests and also to break the taboo. So obviously, dressing as pee and poo cards is not the only way to break the taboo. Another way is to remind that we can close the loop and that wastewater can be a resource.
Thank you very much, Céline, for your presentation. I'm already looking forward to the discussion afterwards. And now, before we go to the second talk, just as a quick reminder, you can always ask questions so we can have a really interesting discussion after the second talk by going to slide.do and enter the code that you can find in the video description. So we'll post it afterwards also in the chat again, so you can really make sure to ask as many questions as you want. But now it's a time to go to the second talk. Our second speaker is Martijn. He recorded his talk yesterday. He's not with the studio with us at the moment, but he'll join us afterwards for a Zoom call for the Q&A. Originally from the Netherlands, he told me that probably water must be in his DNA because he was actually born on reclaimed land that is below sea level. As he will tell you later, he was born and studied in the Netherlands, then moved to Australia and is now also a researcher at Eawag. So, ask questions and we'll go on to the second talk. Thank you.
Hello everyone, my name is Martijn Kuller and today it is my honor to talk to you about stormwater in our cities, or rainwater, and how to turn it from a burden into a benefit. Before I start, let me first quickly introduce myself. I was born in the Netherlands, and since I was a little kid, I've always had a fascination for geography, especially the geography of cities. And throughout my studies and career, I've tried to combine this interest with my other interest in sustainability. So during my PhD at Monash University in Melbourne, I've studied the interface between urban planning and urban water management, and very aptly I graduated back in 2019 in the rain, as you can see in the picture. Because of my fascination with cities, I've lived in different cities, from small, like Wageningen in the Netherlands, to big, like Melbourne and Sydney in Australia. And I'm certainly not the only one, because now half of the population in the world lives in cities. And this number is only going to increase into the future to about 70% by 2050, mainly due to the rapid rise of the cities in Africa and Asia. In Western countries like Switzerland, the urbanization rate is already very high. Switzerland is 74% at the moment. But all these people that live in these cities are under threat. Flooding is by far the most important natural hazard. And over the past 30 years, urban floods have quadrupled, according to the World Bank. The damage caused by floods has increased even more over those 30 years. And this is also projected to increase even further into the future. Now, cities are actually the places where these effects are felt the most, just because of their density of population and density of property that can be damaged. At the same time, cities around the world are grappling with the effects of increasing droughts. In 2018, the Cape Town government announced the coming of day zero, where the water would run out. And at the beginning of this millennium, we had a very severe drought in Australia called the Millennium Drought, where there were very severe water restrictions being put into place. But also here, we're actually for the third time in a row in a drought in spring in Europe, and you can see the effects that it has on my lawn. Heat is another threat. Here on the map, you can see a picture of the city of Zurich in 2017 in a heat wave in June. And you can see that the inner city parts are significantly warmer than the surrounding areas with green space. And this effect is called the urban heat island effect, where cities over daytime capture the heat of the sun and then during the nighttime release it slowly, causing these inner city parts to be much hotter than the surrounding. Now, this particular heat wave actually caused 1,000 people to die in Zurich. The following problem might not resonate so much with people in Switzerland because the waters here are crystal clear, but in large parts of the world, cities are not blessed with these clear waters. So I remember living in Sydney, close to Coogee Beach, which is one of the most famous beaches of Sydney, probably the most famous after Bondi. That after a long dry period, followed by an intense rain, that there would be a newspaper advertisement saying, "Don't go swim on Coogee Beach." And this was actually caused by the stormwater that was released into the ocean, because Coogee Beach is right next to the outlet of a stormwater sewer. And so the pollution that then washes off from the urban services includes mostly phosphorus and nitrogen, which has a negative effect on the biodiversity in water, but also things like heavy metals and even pathogens, which makes the water very unsafe to swim in. Increased urbanization, of course, leads to a decreased amount of green space, which actually has a very significant impact on people's health and well-being, besides, of course, the decline in biodiversity. Now, there are some exceptions of cities that have a lot of green space, such as Moscow, Singapore, and Sydney, where almost half of the city is covered by parks and gardens. But in a majority of cities, this percentage is much lower. And in extreme cases such as Dubai, Istanbul, and Mumbai, this percentage is only 2. Now, all this havoc is caused by two main drivers. The first one being climate change. Climate change leads to more intense rainfall, causing floods, but also longer dry periods, causing droughts. And it leads to more and longer heat waves. Now, climate change is an external driver that local governments, city governments, can't really influence. So that is the bad news. Now, the good news is that city governments can influence the second driver, which is urbanization. And I'm talking mostly about the quality of urbanization in this case, because the quantity of urbanization is a bit more hard to restrict. But the quality of urbanization is something that city planners can actually influence with how they manage the city. And water management is actually a major part of this. In a natural environment, this is what happens to rain. About 40% of it evapotranspirates, then 25% of it infiltrates into the soil and is available to plants to grow, and 25% goes into deep infiltration into so-called aquifers. Then 10% remains, which runs off into rivers. Now, in an urban environment, this water cycle is heavily altered. So of the rain that falls in the city, about 30% is evapotranspirated. 10% goes into shallow infiltration in the soil. 5% goes into deep infiltration, which leaves about 55% to run off directly into rivers. So This heavy increase in runoff makes cities much more prone to flooding, while the decrease in evapotranspiration helps actually make cities more hot because evaporation cools down an environment. And then the decrease in the infiltration actually makes cities also more prone to droughts because there's less water stored in the soil that can be used in periods when it doesn't rain. So in order to decrease all these problems, we want to actually move from the situation on the right back to the situation that is more natural on the left. But how can we do this? One way of doing this is to move away from the traditionally used gray urban water infrastructure, where we put the water literally in the gutter and then it moves to the sewer system and as quickly as possible into the urban waterways, to move to more decentralized green-blue infrastructures. Now, these green-blue infrastructures can simply be parks with a lake or a garden with a pond. But over the past few decades, civil engineering research has focused on designing green-blue systems that are specifically made to improve the processes of bringing the natural water cycle back into the city. These systems such as wetlands, bioretention systems, and green roofs, they retain the water in the city, and thereby it has more time to infiltrate into the soil, it has more time to evaporate and cool down the city, and it can also be used to recycle and actually, for example, irrigate urban spaces like sports fields. Now there's a number of these systems around. For example, these rain gardens that are also called retention systems or biofilters. An example of a rain garden I'm showing here in the picture on the bottom of the slide. This picture I took in Urbanization, where I live. And as you can see, this biofilter is a little bit lower than the surrounding area, so that the water flows into this biofilter instead of flowing into the gutter. And then it goes through several layers of filter media that take out some of the pollutants that can be found in rainwater, in stormwater. And at the same time, they're planted with specific plant types that take up the phosphorus and nitrogen, which is two of the main pollutants found in urban stormwater. And plants use these nutrients to grow. Once the water filters through this biofilter, it can then be infiltrated safely, or it can be put into a sewer and released into the natural waterways, or it can even be recycled and used to do irrigation, for example. Another system that you'll all be familiar with is ponds and lakes. So in the picture on the bottom, you can see a lake that is in Urbanization again. And it takes the water from this residential area behind it, and in a very severe rain event, all the water will flow in the lake instead of flooding the streets of this residential area. And then at the same time, the water will stay in the lake for an extended period of time, which means that the coarse material, the coarse pollutants, will slowly sink to the bottom, and the water that then flows out of the lake eventually back into the natural waterways is cleaner than when it came in. Then a more advanced system are wetlands. In the top right picture here, you can actually see a wetland in Melbourne, and you can see that the water has to follow a specific course, and along this course, different water depths and different plants are used to clean the water, just like the biofilters are doing. Because the water has to run through this course, it also stays in the city for longer, and it, in the end, can then be slowly released into the natural waterways. And finally, we can green up the buildings of the city themselves. In the bottom picture, you can see an example of a green roof. This is actually my bike storage of my apartment. And on the right, you can see a green facade of an apartment close to me. And these systems are actually ideal for places where there's not a lot of space, so in dense urban areas, because they can just be built on buildings themselves. And if they're designed properly, they can fulfill the same function that an urban wetland, for example, does, because they can retain the water, they keep the water in the city, and slowly treat it, clean it, and then release it. Cities around the world have started implementing these systems, although very slowly over the past decades. But they're called different in every part of the world. Here in Europe, they're called nature-based solutions, while in Australia, where I studied them, we refer to them as water-sensitive urban design. In China, they use the analogy of a sponge, which I personally find really apt. So they call it Sponge City, and they're currently investing billions of dollars to turn, I think, 38 cities, major cities, into these so-called sponge cities. In the United States, these systems are referred to by low impact development, whereas in the United Kingdom, they use sustainable urban drainage systems. So it's called differently everywhere, but it all refers to the same thing. All the different approaches and different technologies have a few things in common. They'll use plants, and they retain the water and clean the water. They recycle the water, and they're decentralized and therefore more flexible, increasing the resilience of cities, buzzword. And they have a large number of economic and environmental benefits. So economic benefits include flood protection, which leads to lower damage costs, but also it has actually been shown that houses around rain gardens or biofiltration systems, this study was done in Sydney, that houses are actually tens of thousands of dollars more in value than without those rain gardens. So there's these direct economic benefits. And at the same time, there's a lot of environmental benefits with decreased pollution into our natural waterways, increased biodiversity, and there's of course also the cooling of our cities and the increased amenity of having more green space in your city. That makes a city more attractive and gives people space for recreation. So if we know all these benefits and we have these technologies available to us, why aren't we using them more? Well, the answer is simple. The current traditional urban water systems are underground, while these green infrastructures are above ground, and so they're not so simple to implement, especially in dense existing urban areas. To make these systems successful, there's a lot of different things that need to be considered in the urban planning. For example, what is the local hydrology? Where does the water flow to? What is the slope? But also, what is the acceptance of the people that live around these systems? Will they be able to appreciate these systems? Where is space available? And what is the price of land, and can we afford to build a system there? But on the other hand, also, where do we need all these benefits that we get from the systems? Where can we use the recycled water, for example, to irrigate sports fields? Or where are the hottest spots in the city that we can cool down using these systems? Where is there a big lack of green space, and where could the city really benefit from increasing this green space? And even where are biodiversity hotspots? So all these things need to be taken into consideration when we place these systems in the city. Because the planning for these GreenBlue systems is so highly complex, in many cases, urban planners resort to what they know, which is just implementing gray systems, sewer systems. And even if they implement green-blue systems, they often do it very randomly. So they just place them wherever they find space or wherever they're redoing a park. So because of this, a lot of people in academia have started thinking of ways to help urban planners improving their planning processes. And one of these people was myself in my PhD. And what I've come up with is a very simple tool, model, a spatial tool that is called Santo, a spatial suitability analysis tool, which gives urban planners this map, which you can see here, that has a simple color code indicating what are the very highly suitable and the less suitable locations to implement a specific green-blue system in the city. Slowly, cities around the world are becoming more green-blue, and the good news is that everyone at home can actually contribute, for example, simply by removing tiles from your garden and putting a plant in place. I know in my home country, they actually have a program where you can bring tiles from your garden to the municipality, and in return for these tiles, you get free plants to put back in your garden. Recently, only like 2 weeks ago, I saw on the Swiss news actually that the city of Zurich is also implementing a big urban greening program, which I was really happy to see. Their focus is more on urban cooling for the hot summer days. But the principles are all the same, and the increase of green-blue spaces will also help with all the other issues that cities are facing. So with that, I would like to end, and you can reach me through email and look me up on LinkedIn. I'm happy to answer any questions that you might have.
Thank you, both of our speakers tonight, for the very interesting talk. I really enjoyed listening to your presentations. And now we can go over to the discussion. And just as a reminder, especially for the second talk, feel free to ask questions. You can find all of the information in the video description. And now we're also connected virtually to Martijn, so welcome to you being live here with us.
Thank you. Thanks for having me.
Yeah, it's a pleasure. So my first question just goes to Céline about her talk. In the end, you talked about how we should rethink wastewater, and wastewater being a pretty large taboo in Switzerland. So how could we increase the social acceptance of wastewater in the future?
Thank you for your question. So I think it's a very complicated topic, like social acceptance in general. So there is a whole department working on that at Eawag. But I think already that people realize it's a resource, it's already a good step, and that we talk about it like I said in the talk, it's not necessarily something people want to discuss. So talking about my job is, well, some people are open with that, but it's not so easy. So opening the mind of people and then make them realize it's a resource, I think it helps a lot. So this type of communication, and then there are obviously articles in journal on the work of Eawag. Also, for example, in different cities like San Francisco, they are trying to implement water reuse. So they make a lot of work to make people accept this topic.
Thank you for your answer. Very interesting, and maybe connecting to that topic, how to go on in the future. We had one question about how we could go on planning cities in the future. Martijn, to you, one person asked, well, it's probably easier to implement these systems in new cities, in new areas, but how can we use existing infrastructure to really implement these systems and improve the life and the green areas?
Yeah, that's a very good question, and that's been asked a lot by urban planners as well, actually. What you can see at the moment is that especially in new developments, so urban growth areas, it is a lot easier to implement these systems because you can start from scratch. So you can make space to implement these above ground green systems. But in inner cities, especially in Europe, this is a lot more challenging. In Europe, cities are very old and dense, and so it's not easy to make space. And also, we don't really have the means to find how we can implement them in these dense spaces. So it is definitely true that it is a lot more challenging, and this is one of the reasons behind my research, actually, which is taking an existing cityscape and then looking for the best locations or opportunities to implement these systems. And there's always something that you can do because there's these systems that are on the roofs, there's these systems that are on walls, and these systems, some of these systems are very flexible, so you can make them as small as you want. For example, a bioretention system. So there's definitely things you can do, but yeah, I agree. It is very challenging in developed cities.
And maybe just to get a personal feedback or from you, what do you think is the leading city worldwide in the GreenBlue implementations?
I think there's a number of cities leading, and I probably don't know all of them. Personally, I've studied this for my PhD. I did my PhD research in Melbourne, in Australia, and this is definitely a leading city in the world. This is also the Monash University where I studied, is the university where the water-sensitive urban design concept was actually developed. But I also know that in the United States, there's a few cities leading in this. I think Portland is one of them. And currently, also in China, they're developing a lot of these so-called sponge cities. So China is starting to become leading in this field as well. In Europe, I don't know if there's really leading cities. I know Rotterdam in the Netherlands is also working a lot on it.
So the Netherlands is the way to go.
Always.
Thank you. So the next question to you, Céline, how do you think difficult is it to scale up a system as you have described, and what are the perspectives here for coming back to Switzerland, maybe in the system that we have here at the moment?
For Switzerland at the moment, we are not really in a restricted resource environment, so water is not really hot topic, I would say, in terms of availability. So at the moment, it's really marginal for Switzerland. So it's at the research stage, and I don't know. Like for example, WUNA is trying to make this process mobile, and they have an in Biel there is like tennis field where they collect urines. And then with their mobile process to produce the fertilizer, WUNA is going there. So they try to adapt to the demand of Switzerland. So it's kind of marginal. And also the mountain huts also can be subject to this type of decentralized system. But it's not really a need, it's not an emergency like it is in other cities. And for upscaling, so here I presented a concept about buildings, and I think we will stick with the traditional wastewater treatment plants also, because it's important to control the quality of water which is released in the environment. But new building can be subject to these types of technology. And once again, I take the example of San Francisco. Now every new building, so there is a law, and every new building should be equipped with a grey water collecting system and recycling system. So it's possible for new buildings and in places where there is a lot of constraints about the resources. But for at the moment, for Switzerland, it's not. It's a bit marginal.
Okay. Thank you. And as I've seen here in the chat, there's also a lot of interest in the tool that you, Martijn, have developed during your PhD. So maybe one question is whether it's also available for Zurich, but maybe people are also interested in how precisely it works and what the idea behind the tool is.
I'll try and give you a short answer to that, which is not easy. The first question, is it available for Zurich? Yeah, in principle, it's available for any city in the world, but it has to be set up for each location. So you need to collect all the data for it. And these are all secondary data sources, so you don't have to actually go out in the field and collect the data yourself. You just need to get the data from municipalities, for example. And then the second question, how it works. So it uses a technique that is called GIS MCDA, which stands for Geoinformation Systems, and then MCDA stands for Multi-Criteria Decision Analysis. So what it does is it takes all these different factors that I discussed in the presentation. So is the slope suitable? Is there space available? How is the acceptance of the local population? Where are all these benefits necessary? It takes all these different criteria, as we call them, and then it uses different techniques to combine them together to come up with a final suitability score. So this final suitability score is then presented on the map that I showed in the presentation as a color. So red means the least suitable location and green means the most suitable location. And then besides that, what you can also do with Santo, with the tool that I developed, is that you can click on the map on a certain location that has a particular color that you're interested in, and then it actually gives you a summary of the reason why the suitability is as it is. So it explains to you, this is a red area because the slope is much too steep, so you can't implement something here. Or this is a green area because of other reasons. So it also gives you this opportunity to get explanations.
Thank you. And now briefly giving it back to you, Martijn. So suppose we have used your tool and implemented such a system. One question that came up was about the maintenance of these zones. How do they compare, and what is your personal stake on this?
Yeah, that's also a very good question. Actually, one of the main issues of why these systems are sometimes, or why there's resistance to the implementation of these systems. Because the maintenance is something that we don't have a lot of experience with. So we don't really know how to do it, who should do it as well, because your regular green areas are maintained by municipalities and by special services run by municipalities. But can they also maintain these green systems that have all this technology in them? This maintenance is not cheap. So this is one of the reasons that people often, or planners often, resort to the things that we know, which is these concrete pipes under the ground to get rid of our water. But we forget that they also need maintenance, and they also need re-implementation after a while, which is also very expensive. So it is also a matter of political will, I think.
Thank you. Interesting insight. So I would like to break up your topic here for a moment and go back to Céline's talk. So always with new technologies, there's the question about the potential risks that we have. So I would like to ask you whether the risk using fertilizers that are made from urine, considering certain traces, for example, from antibiotics or the contraception pill. How does that measure out in reality?
So it's a very good question, because it's a hot topic in Switzerland. You have a law where you have to remove these micropollutants from the wastewater in general. So in urine, most of the antibiotics or pharmaceuticals are in urine. So it's a very good question. And the process that was developed by Eawag and is now optimized by Vuna Then there is a distillation step, which removes all trace of contaminants. And since it was also licensed as a fertilizer by the Swiss Federal Office of Agriculture, they had to show that they remove all of these contaminants. So there is absolutely no risk. And then with the distillation, you also remove the pathogens. So there is really no risk for health. This is why we can basically use it to grow vegetables.
Okay, thank you. And there was, as I've seen, another question about risk, going back to you, Céline. So what are the risks using bacteria to use them to break down certain substances that we don't want in the water?
So the bacteria, they are on the dirty water side. So theoretically they don't pass through the treated, like the membrane. So we don't find them theoretically in the treated water. But to be sure that before redistributing this water, we really have to make sure there is no bacteria. So most of the time after the membrane, there is another disinfection step. But it's also depending a lot on the type of water reuse you do. Like if you do potable water, then it's like the regulation is much more stringent. And then if you reuse it for watering, for example, then it's a bit less stringent, I would say. So there is always a disinfection step, but these bacteria I was talking about, they stay on the dirty side of the water. So they are not a problem for the water quality.
Okay, interesting. And so there was another question about the source separation. This is not your specific area of research, but maybe if you have some insight in how the feces are separated from other substances, like for example toilet paper, does that need an additional step in the preparation, or do you know anything about that?
So I am not a specialist on this, but I use the toilets at Eawag, and we use toilet paper. And I think so people have to be aware that they cannot throw anything except toilet paper in the toilets. And I think in the process of separation of dewatering the feces, I think it's not really a problem to have toilet paper because it's also a source of carbon. So it will just be separated with the feces and then pressed as pellets. I think so. But yeah, I'm not really the specialist of this. On the Eawag website, there are more description about the different streams and what is done.
Okay, good. But maybe continuing on the subject, I know you're not an expert in, but there was a question about how to recover the phosphorus from the feces. Is that possible to get all of the nutrients and all of the interesting elements, like for example phosphorus, out of the feces?
I think that, so once again, I am not really an expert on that, but I think that a big portion of the phosphorus is present in urine. So this is why a big effort was made on urine valorization. It contains also the nitrogen. And the feces, since it's a main source of carbon in wastewater, I think this is why they selected this valorization as pellets for the heat, and also to have something a bit complete like agriculture, water and heat. But I'm not really an expert on this topic.
Thank you very much. I'm maybe going for coming to an end slowly but surely. I would ask Martijn a question. Like, we have talked quickly about the historical centers in cities, that this is really difficult, but still people are wondering if it is possible. Have there been examples, and how can we try to implement these cities in, for example, historical centers in Europe?
Yeah, it's a tricky one because there's often in historical centers there's also a lot of regulations around historical buildings and places. So oftentimes you can't really do so much. You can't make a green wall on an old building. And I think also most people wouldn't want that. So I think really in historical inner cities, maybe the only thing you can do is implement these small rain gardens in streets. Also, historical cities centers have green patches now, like trees and little gardens, so you can make them work for the urban water management more. Another system that I didn't mention is a tree pit, which is basically just a tree, but it has these filters inside as well, and it's actually designed to capture the water. So these kind of systems you can still implement. But I think we also need to realize that the biggest problems aren't necessarily related to these historical city centers, because these are only very small parts of our cities, and by far the largest parts are the residential suburban areas around the cities or around these historical centers. So I think it's tricky to implement it, but it's not necessarily a huge problem, I would say.
Thank you for your answer. And now I would just like to give you one last time the word. What should people really take away from your presentation, your answers, and what can maybe people at home do to help our cities grow and our water to be pure?
Should I start?
Yeah.
Well, I mean, my message is that water can be a resource. Wastewater can be a resource of water and other types of nutrients. And that, just be ready to talk about it and not feel that it's too much of a taboo. I think it's already a good take-home message.
Super, thank you. And Martijn, for you, what would be the last words apart from appreciating all the green spaces in Zurich Oerlikon?
Yeah, first I would like to say that actually there's also a very interesting overlap between our research, because grey water can actually also be used to feed into some of these systems like green walls, and you can treat the grey water that way, just like you treat the stormwater. So there's definitely a lot of opportunities, and I would like to say everyone can also play his part. By just, if you have a garden, just remove the tiles from your garden and put a plant in. That already helps massively, because the water won't run off anymore, but it will infiltrate in the soil, and your garden will be a lot nicer as well. So I would say you can do that tomorrow. And maybe next time you walk past a lake or a little garden, you can start thinking about how cool these systems are and what they actually do for our cities.
Thank you. So to everybody watching, you know what to do on the weekend. But I also know what you should really do in the next 5 minutes, which is namely give our speakers of tonight feedback. Namely, if in 2 or 3 minutes on Slido, the same code as for asking the questions will then implement a feedback form that you can just quickly fill out what our speakers tonight, who have been great, have done really well, and where they can maybe also improve in the future. So it's a pleasure for me to have you here, and such an interesting topic. And the nanoTalks, we are going to be back in 1 month, probably also live streamed here from the studio. Thank you again very much for listening, and have a nice evening.
Thanks everyone.
Bye bye.
Thank you.